Okay, thank you. Thanks for the introduction. And I would like to thank the organizers and the committee for offering me this great opportunity to present our recent work on non-Hermitian quantum walks and the topological properties. Also, I would like to thank you all for your participation, and I hope you enjoy this conference. So this is the outline of my talk. First, I would like to give a brief introduction to the parity time symmetry quantum walks briefly, and then I would show our recent work on experimental observation of non-Hermitian skin effect and the investigation of non-Bloch, the exceptional points. Finally, I will introduce the very recent work on the simulations of non-Hermitian semi-metals and non-Hermitian quasi-crystals. So first, I would like to give a brief introduction to quantum walks. A quantum walk is just a generalization of classical random walk. So actually, there are two kinds of classical random walks, like this continuous time random walk. For example, the Brownian movement, and there's another kind of classical random walk, discrete time classical random walk, right? Like this Golden board. Or you can imagine a simple example. A person holds a coin and starts from the original point of a line or lattice. She or he flips the coin to decide which direction. If it's a tail, then he walks towards left. Otherwise, a step towards right. This is a discrete time classical random walk. Correspondingly, there are two kinds of quantum walks. In this talk, I will only focus on the discrete time quantum walks. So now you're gonna see the difference between the classical random walk and quantum walk. If we ran a classical random walk and a quantum walk for the same number of the steps, we will obtain completely different probability distributions. A Gaussian or a Gaussian distribution for classical random walk and a ballistic distribution for quantum walk. For a quantum walk, the spread speed of the distribution has a quadratic enhancement, so we can use quantum walk to develop quantum algorithms, like searching algorithms. And in our group, we use single photons or entangled photons and linear optics to realize quantum walks. So the coin can be realized by the polarization of single photons, and the walker can be realized by the spatial modes of single photons. So the condition of position shift can be realized by the beam displacers, and the coin flipping can be realized by wave plates or set of the wave plates. So there are some our recent experimental result of quantum walks. So now I'm gonna talk about the parity time symmetric quantum walks. So for non-Hermitian systems, the eigenenergies might not be real anymore. However, if the system possesses some symmetries like parity time symmetry, the eigenenergies are still real. So we can realize them in our experimental setup. So the non-unitary dynamics can be simulated by quantum walks. Then we can compare with the previous experimental results with classical light. In this experiment, we use single photons. So we want to observe PT symmetry in the real quantum regime, such as single photon levels. So this is the motivation of this work. So it is proven in a theoretical paper published in 2016. The non-unitary quantum walks with alternating gain and loss possess PT symmetry. So this is the Flaccetta operator, and the C is the coin flipping operator, and S is the conditional position shift operator, and G is the gain operator. And the gain operator or the loss operator introduced the non-hermiticity, and this is the PT symmetric operators here. But actually, because we want to use single photons to realize the experiment, so it's difficult to realize the loss. Sorry, so it's easy to realize the loss of single photons, but it's difficult to realize the gain of single photons. So in our experiment, we use the alternating less loss or more loss to replace the alternating gain loss to realize this non-unitary quantum works. So this is our Flaket operator, and L is the loss operator. L prime is another loss operators. And with a proper mapping, we can prove this Flaket operator also possesses PT symmetry. So this is what we're gonna realize. This is our experimental setup. Non-unitarity or non-hermiticity is introduced by the loss operator, by photon loss in our experiment. And the loss operator is realized by this kind of partially polarizing beam splitters. So this is the phase diagram under the periodical boundary condition. And this white and gray regions represent broken PT symmetry phases with complex eigenenergies, whose real part is either 0 or pi. And the color regions, like the pink and yellow and blue regions, represent unbroken PT symmetry phases. And this green and blue and red curves represent the boundaries between broken and unbroken PT phases. Actually, they are also the boundaries between different topological phases. So you can see all these numbers are just Whiting numbers. And there are two numbers because the Flaket operator has two different time frames. So we have two different topological invariants for each phase, for each topological phases. So compared to the unitary quantum works, the region where this kind of region, okay, the region where the topological numbers are EU defined, extended from lines to a finite region. And the area of the regions depends on the loss operators or the loss parameters. Okay. So we're going to show the behavior of the PT symmetric quantum works in the unbroken PT phases. So we first choose the coin parameters, make the system in the PT unbroken regime, like this 5-star simple. And then we can see the energy gap are still open and all the eigenenergies are still real because they are in the PT symmetry unbroken phases. So the eigenvalues of the time evolution operators are in the circle. And this is our experimental result. So you can see the measured probability distribution is still ballistic, which is similar to the unitary quantum walk. Okay, now we change the coin parameters and let the system to be at the exceptional point. So it's just between the PT symmetry broken and unbroken. So you can see that the energy gap is just closed, but all the eigenenergies are still real or 0. Okay. So you can see that the probability distribution is still ballistic here. That's our experimental result. So you can see the probabilities distribution is still ballistic, but only different is the peaks are squeezed a little bit, but they are still ballistic. Okay, now we continue changing the coin parameters and the system is now in the PT broken regime. Okay, so you can see that the energy gap is closed at either 0 or pi. And some eigenenergies are not real anymore. So you can see this dashed line. They are the imaginary part of the eigenenergies. So you can see that for some eigenstates, the eigenenergies are not real anymore. So this is our measurement experimental result, measured probability distribution. So you can see that it's not ballistic anymore. It's nothing like the unitary quantum walk. It's showing the Gaussian distribution. Okay. Now we're going to talk about more interesting topic. That's the topological phases in the PT symmetric quantum walks. So at this kind of quantum walks, also So as you might know, the unitary quantum walks possess chiral symmetry and time reversal symmetry and particle hole symmetry. So for the unitary quantum walk, we also expect some topological phenomenon. But in the PT symmetric quantum walks, chiral symmetry is broken. So whether or not there are still similar topological properties in the PT symmetric quantum walk is still was an open question, and we answered it. So at this kind of quantum walk also possess pseudo-hermiticity, which could drive the topological phenomenon. So we want to observe the topological edge state. Then we need to create some regions in the real space. So we create 3 regions in the position space. We create 1 inner region and 2 outer regions. So when a walker walk from one region to another in the position space, in the real space, okay, the parameter makes the system in the different topological phases. Then we will observe the localized probability distribution, which caused by the dynamics of the edge state. So now we fix the coin parameters for the inner region and change them for the outer region. So first, we choose the coin parameters for both inner regions and outer regions belong to the same topological phases with the same Whiting numbers. And actually, no edge state is expected because when the walker walks through in the position space, nothing changed. They are still in the same topological phases. So no edge state is expected. And that's proved by the probability distribution. So you can see that up to 7 steps, we still observe the ballistic distribution and no localization behavior. Now we change the coin parameters for the outer region. We fix that for the inner region and change for the outer region. So you can see that this is for the inner region, the black circle, the black dot, and the red square for the outer region. So you can see that one of the Whiting number is different between the 2 regions. So that's we expect the existence of the topological edge state with real part of the eigenenergy equal to 0 or pi. So we observe the localization of the walker. Let's see this is the probability distribution. So we can see that for each step, the walker is localized at the boundary, which is the boundary at x equals to 4. So you can see that the localized probability increase with time. This is different from the unitary quantum walk. That's because when the walker passes through the different phases, it also passes through the broken PT symmetry phases. So which caused the light density increases with time in the exponentially. So that's why we can observe the localized probability increase with time. Now we still continue changing the coin parameters for the outer region. So we can see that both topological numbers are different for this case. And that's why we could expect the existence of 2 kinds of topological edge state. So you can see that this is our probability distribution. And this probability increase with time. And the probability of the phonons being measured at x equals to 4 and x equals to 6. So this oscillating behavior with time is a signature of the existence of 2 kinds of topological edge states. Now, actually, one of the major features of topological properties is their robustness against the perturbation. And also in our experiment, we show the edge state are robust to the symmetry preserving disorder, including the static disorder and dynamic disorder. And also the edge state are robust against the symmetry preserving small perturbations of the system. So when we're wearing the the coin angles or the coin parameters and maintaining the topological numbers, we observe similar probability of which confirms with the continuing existence of the topological edge state. So now we're gonna talk about our second work. That's the observation of non-Hermitian skin effect. So we consider a non-Hermitian system with open boundary condition, and all the bulk states become localized. That's so-called non-Hermitian skin effect. So in this case, the bulk edge correspondence for the Hermitian case does not work for the non-Hermitian system with open boundary condition. Now we need to correct the bulk edge correspondence for the non-Hermitian system driven by the non-Bloch band theory instead of the Bloch band theory. So that's the motivation of this work. This is our experimental setup. So you can see that we use the interference-based measurement, then we can measure or we can reconstruct the evolved state. And this is the evolution operator, also our Flaket operator, and M is the partial measurement, which introduced the photon loss and also introduced the non-hermiticity. And this is the boundary condition for a Hermitian Hamiltonian with gamma equals to 0, and one can easily see. So this is the boundary condition. In our experiment, we used domain wall boundary condition instead of open boundary condition, but actually we could observe the same experimental result with this two different boundary condition. And this is the eigenstate. So you can see that with gamma equals to 0, that's for the Hermitian quantum walk. You can easily distinguish the bulk state that's represented by these black curves, and from the edge state, that's the red curves. So the edge state are localized at the boundary, and the bulk state are not. Right? That's for the Hermitian cases. And for a non-Hermitian Hamiltonian with gamma increasing, gamma equals to 0.05 and 2 gamma equals to 0.5. So with gamma increasing, except for the edge state, all the bulk states are also localized at the boundary. That's so-called non-Hermitian skin effect. So with the non-Hermitian skin effect, it's difficult to distinguish the bulk state and edge state. So that's why we're gonna observe this kind of behavior, which is not exist in the Hermitian case. So this is our experimental result. So you can see that by choosing proper parameters of the time evolution operator, we make sure there are no topological edge state in either Hermitian case or non-Hermitian case. And for the Hermitian case, you can see that we choose the loss operators gamma equals to 0, and the probability distribution shows perfect ballistic behavior and no localization is observed. But for the non-Hermitian case, although there's no edge state, but still we can observe the localization behavior occurring at the boundary. So that's so-called non-Hermitian skin effect. So in our experiment, we prove there is a non-Hermitian skin effect. Now we're gonna show the eigenspectrum. So this is the eigenspectrum, which is calculated with the periodical boundary condition. And this is the Whiting number. So the dashed line are the Bloch-Whiting number, which is calculated by the Bloch band theory and periodical boundary condition. And the solid line, the red and the blue solid lines, are the non-Bloch Whiting number, which is calculated by the non-Bloch theory and open boundary condition. Okay, so you can see that for the Bloch Whiting number, there's a -12, right? So that means for this case, it's not EU-defined. The Whiting number is not EU-defined by the Bloch band theory. So we need to correct them. We use the non-Bloch band theory to redefine the Whiting number. And we can get 0 for the topological trivial and -1 for the topological non-trivial. Okay, so this is the definition, and now we can show the probability, sorry, we can show the experimental result of the total probability distribution for the last step. So we choose the parameters represented by the blue dot. You can see that with the Bloch band theory, we get -1/2. So that means ill-defined. We cannot tell if it's topological trivial or not trivial, right? But for the non-Bloch winding number, we can easily tell there is no zero mode edge state, but there is a pi mode edge state, because for the blue light we have this -1 for the winding number, and that's our experimental result. We can observe there's a localization for the pi mode. That means there's a pi mode edge state, and there's no localization for the blue for the red one. That means there are no pi mode there's no zero mode edge state. So this is our experimental result, which can confirm that only pi mode edge state exists, and also we confirm the non-Bloch band theory works well for the non-Hermitian Hamiltonian with non-Hermitian skin effect. Okay. Now this is another experiment. So that's the non-Bloch PT symmetry and exceptional point, and this is our this figure shows the imaginary part of the Posey energies, and you can see that the blue and gray lines represented the open boundary condition and non-Bloch spectra, and the theoretical boundary condition and the Bloch spectrum. So you can see that the blue non-Bloch spectrum feature an exceptional point or critical point, but the gray Bloch spectrum remains all complex valued eigenenergies. So we're gonna use our experimental result to prove which one is correct. If we observe a PT phase transition, also if we observe an exceptional point, then we can confirm the non-Bloch PT symmetry or non-Bloch band theory works well for this system. If we didn't observe a PT phase transition, that means the Bloch band theory is still working. Okay, so we're gonna show the experimental result. So the yellow and blue regions are broken and unbroken PT symmetry respectively, and the parameters are indicated by the red cut here, by the red cut. With θ2 increasing, the phase change from the PT unbroken to PT broken, so which is confirmed by the experimental result. This is our experimental result. So this is the probability for the last step, step 7. Okay, the probability increase exponentially in the PT broken phases. So that means we observe the exceptional point occurs at θ equals to 0.413. When θ increase larger than this critical point, then we could observe the exponential increasing of the probability distribution. And also from this experimental result is more clearly, when varying the parameter of the coin, we observe a PT phase transition and the non-Bloch exceptional point. That's our experimental result confirm the non-Bloch band theory works well for the PT symmetric system under the open boundary condition with skin effect. So with these two kinds of experimental results, we can see that for non-Hermitian system, in the under the open boundary condition, if we could observe a non-Hermitian skin effect, then we should use the non-Bloch band theory an open boundary condition to calculate the eigenspectrum, or to calculate the calculate the topological properties. And in this experiment, we directly detect the non-block topological invariant. That's the winding number. So we use the Carroll displacement in a generalized Course momentum time domain following a quantum quench. Then we can detect the topological winding number directly. So this is the phase diagram. So we can see that if we use block band theory and non-block band theory, we can calculate different topological invariant. But in our experiment, we observe the exact values of the Carroll displacement, which confirms the non-block topological invariant are well defined, and the block topological invariant are not well defined. So this is the experimental result. Now we're going to talk about something a little bit different. So this is another work. Actually, we didn't use quantum walk. So the quantum walk is in our experiment is more complicated. So actually in this experiment, we just use very simple setup to simulate non-unitary quantum dynamics with single photons. And we show the information flow between the parity time symmetric non-Hermitian system and the environment. So we observe the oscillations of quantum state distinguishability, that's the entropy, and the complete information retrieval or revival in the PT symmetric unbroken regime. So in the PT symmetric unbroken regime, because there is a balance between the loss and gain, between the information flow from the system to the environment and from the environment to the system. So we can observe the information revival. But for the PT symmetry broken regime, because the balance is broken, so we observed exponential decay of the distinguishability. And more interesting is the critical point, is the exceptional point. So we observe the power law behavior at the exceptional point. So this is the very simple experimental setup, but we can still simulate the dynamics of the PT symmetry quantum evolution, and we observe the information flow to characterize the critical phenomenon. So this is another experimental result. This is the Kibble-Zurek mechanism. So Kibble-Zurek mechanism was originally proposed for the domain formation. And experimentally, the theory has been confirmed in the Hermitian system. And now we want to prove that it also works for the non-Hermitian system. So we use single photon interferometry to reconstruct the non-Hermitian Kibble-Zurek mechanism and its distinct scaling behavior for exceptional point, okay, by simulating the defect population behavior. So this is our experimental result. So you can see the experimental result showing here. We're also able to realize the high order, and in this experiment, we realized a high order exceptional point. So we realized the 4th order exceptional point. And you can see that this is our experimental result. So you can see that the experimental result confirmed the Kibble-Zurek mechanism also works for the non-Hermitian system and can well predict the critical phenomenon at the exceptional point. At either second order exceptional point or 1st order exceptional point, we also observe the different power law behavior. So that shows the same result from the Kibble-Zurek mechanism predictions and quantum mechanism predictions. I think I only have 10 minutes, and now I'm going to show you another experimental result. This is also our recent experiment. We experimentally simulate the non-Hermitian semimetals characterized by the topological properties of their node band structures. We implement the non-unitary time evolution, and we can prove the complex eigenenergies of the corresponding non-Hermitian Bloch Hamiltonians here. That's the Hamiltonians. And we study in details of the topological of their exceptional lines and exceptional surface. So in this experiment, there are interesting properties is that we focus on two distinct types of non-Bloch semimetals, and two-dimensional semimetals and three-dimensional semimetals. And for the higher dimensional semimetals, like the three-dimensional semimetals, we show that it's very different from the Hermitian case, because in the three-dimensional semimetals, processing symmetry-independent topological exceptional lines. So even without any symmetries, it is still very robust to the disorders and perturbations. So this is very different from the Hermitian case. And for the last work, I'm going to show you a different experimental setup. Before, we used the bulk optical elements, and now we use time being to realize our non-unitary quantum works. So use in a time domain. This is our Flockade operator. So experimentally, in this experiment, we experimentally simulate the non-Hermitian topological Anderson insulator with disordered photonic quantum works. And we characterize its localization and topological properties. So for experimental implementation, we adopt a time multiplexed, so the time domain scheme. And the Walker is encoded in the time domain of the photons, which is different from the spatial mode we usually use. So the photons are coupled in the in and out of the interferometric network through a beam displacers here. So the coin operator is still carried out by the wave plays and dynamic EOM. And the shift operator, that conditional position shift operator, is realized by splitting the light or the photons using the polarizing beam splitters into two different length fibers, the longer one and the shorter one respectively. As such, the position of the walkers are encoded into the polarization dependent temporal shift within the time steps. And now so this is our experimental result. We focus on the competition between the Anderson localization caused by the random disorder and the non-Hermitian skin effect, under which all the eigenstates are squeezed towards to the boundary. So there are two kinds of characterizations. There are two kinds of localizations, which one of which caused by the Anderson localization, the other is caused by the non-Hermitian skin effect. Now we're going to show the competition between them. So the two distinct localization mechanisms promote like this. So we choose gamma equals to 0 and W equals to 0. W is the strength of the disorder, and gamma is the strength of the non-hermiticity. So when the gamma equals to 0 and W equals to 0, that means we have the standard quantum walk. And you can see that that's the Lyapunov exponent. Is the behavior.
PENG.
Sorry.
Yeah.
Okay.
Together with questions you ask, like, yeah, you have like 1 minute to go.
1 minute. Okay.
Yeah.
Okay. Yeah, I'm gonna finish this. Okay, so you can see that we show the competition between the two localizations. And for the non-Hermitian skin effect, we see the population fluid, the localization is caused by the population fluid. And it would make the Lyapunov explanation not symmetry anymore. But when we increase the strength of the disorder, it is caused by the localization is caused by the Anderson localization, and the behavior is symmetry again. So we show that the behavior, the competition between the two kinds of localization in this experiment. And also in this experiment, we measured the local marker, which is the topological nature of the non-Hermitian topological Anderson insulator. So we use the the average Carroll displacement. We measure the average Carroll displacement to indicate the local marker. That's the topological invariant of the Anderson insulator. And the last page is something like we simulate the non-Hermitian Corsi crystal. And in this experiment, we observe three triple topological phase transitions. That's skin effect and no skin effect, and PT broken and PT unbroken, and the localization and dislocalization. We observe triple phase transitions at the same parameters, and also we observe the mobility edges in this experiment. Okay, now I'm gonna finish this. So I would like to thank our collaborators, and all the experiments are done by my group. And also I would like to thank our collaborators in the theoretical part, as Professor Wei Yi at University of Science and Technology of China, and Professor Zhong Wang at Tsinghua University, and also Hideaki Obasa from Hokkaido University, and Professor Masahiro Ueda from the University of Tokyo, and Professor Master from Max Planck Institute, and Professor Jan Budish from Dresden. And also I would like to thank Yogesh. And thank you very much for your participation and for your attention. Okay, so I would like to see the questions. Would be helpful. I can get the slide of this. Okay, are there any other methods to realize? Oh, yes. There are some. Yes, there are some other methods to realize non-Hermitian system, as I showed in this slide. There are some much simple. This one. So this one, we just use two beam displaces, and we just use a very simple interferometer to we just use MZ interferometers to simulate this kind of non-unitary dynamics. And this is much simpler. This is just like we realize a one-step quantum walks. And also there are another methods like the cold atoms. They can use the cold atoms to realize the system, the non-Hermitian system. They can even measure the eigenenergies of the system. Because we use the photons to realize the non-Hermitian system. So we cannot directly to realize the Hamiltonian or the lattice. We need to use this kind of dynamic properties to characterize the spectrum of the Hamiltonian. So that's why we need to use the quantum walk, because it shows the dynamics of the system. But if you have the qubit, or if you have the lattice, like the optical lattice with the atoms in, then you can directly simulate the non-Hermitian systems. You do not need to use this dynamic of the system, which is quite difficult. Okay, what is the dimension of the state of the Hamiltonian evolved? In this experiment, the Hamiltonian is two-dimensional. And in our experimental of the quantum walk is 2 by n. 2 is for the coin. Coin is two-dimensional, and n is for the position of the walker. Like, for example, like this one, because we realize the 7th step, then 7 times 2 times, so it's 14 by 14. That's the dimension of the walker, and 2 is the dimension for the coin. Okay. Because it's difficult to construct observed in a high dimensional, how do you address this issue? Observe in a high dimensional. Depends. For some observable, it's not so difficult because we can realize a high dimensional system, right? For our system, the coin is two-dimensional, but for the walker, it could be higher dimensional. So it depends. I think we could construct a higher dimensional observables, like the Carroll displacement.
Sorry, Peng, there's a question in the chat, not in the Q&A.
Yeah, okay. Your quantum. I'm looking at that. Your quantum work experimental demonstration seems to have a lot of linear. Yes, linear optical element. Do you build a setup goes to trying different arrangements, or do you have an optional way to doing this? Use quantum machine to. Well, actually, yes. We will use the quantum machine to. So I think we had a paper published in PRA last year. We used quantum machine to build arbitrary non-unitary operations. Yes, we use this one, but still we use optical elements. So we use linear optical elements to build a single qubit rotation and 2 qubit non-unitary operations as a set or as a segment. And then we use machine learning to choose the different set of this kind of gates and to trying to realize more or arbitrary two-dimensional or arbitrary 2 qubit non-unitary gates, something like that. We had a paper last year, so I could send you the papers. I also see your quantum works use single photons. Why use? Yes, we could use. So if you only care about the, let's say, single particle, for example, if you only care about the quantum work with single walker or single coin, of course, you can use the weak laser. And actually, we use the weak laser here in this time being quantum walk.
Okay.
In this time being quantum walk, yeah, we use the laser, the weak laser. But if you consider a multiple walker, then you need to use entangled photons. Then you cannot use weak laser to replace the single photons. So that's my answer. Okay, thank you.
Thank you very much, Peng. People would like to have your slides, so it would be good if you will be happy.
Sure, I can send you. Yeah. I can send you the slides. Yeah.
Okay. Do you have any question from the audience here in Kigali? Okay, so let's thank Professor Peng XUE once again.
Thank you.